Quiz. Let's bring in my favorite student. Good old Anne. You can ignore sig figs. I used to really penalize kids for sig figs, and you know what? It's not that important to me. I've taught you the skill, but whatever. Number one, how much work? Well, work is force times distance. It's also the area under a graph, but I don't see a graph. You are also going to get, in a couple of lessons, a third definition of work, actually the best definition of work, and it's the one that I use when there isn't a force and a distance, or a graph. But for now, I have a force. We're pushing a car, so the force and the distance are in the same direction. It's going to be 767 times 28. Oh, I get to show you some of my favorite videos today, too. Cool. 767 times 28. Do you get 21,476? Excellent. You pause the video for my latecomer. I'm going to go 21,500. I'll go to 3 sig figs. But if you wrote 21,476, that's fine. 21,500 joules of work. Is that a lot? Again, work is not what makes you tired. Power, how fast you do the work. That's oh, well, how much power? Power is over time. I'll use my full value, 21,476. 21,476. Over 58. You know what? I don't think they're generating much power because 28 meters is not very far, and if it takes them almost 60 seconds, they're not pushing this car terribly fast. I'm expecting a fairly small answer. Yeah, 370 watts. Okay. These are 1 mark each, so I guess I'm going to kind of go all or nothing. Number 2, A, what work is force times distance, and we're raising, you know what? It's going to be mgh. Really what you're doing is you're giving this object potential energy. You're doing work on the object. It's going to be 688 kilograms, that's pretty heavy, times 9.8 times 2.8 meters. 688 times 9.8 times 2.8. 18,000, I'm going to go 18,900 joules of work. Suppose it does this in 73 seconds. Not very fast. To move 2.8 meters in 73 seconds is pretty slow. Although this is pretty heavy, maybe it would move and kind of inch its way up very, very slow. How much power? Power is work over time. I'll use my full value, 18,878.72. 18,878.72 divided by 73 seconds. Do you get 200, how about 259 watts? Watts. Hey, is work a vector or a scalar? Is energy a vector or a scalar? Scalar. Is power a vector or a scalar? Scalar. Is momentum a vector or a scalar? That's why we had to pay so much attention to east and west and negative and positive. Okay. Units, joules. You could write out the word joules, J-O-U-L-E-S. Mr. Duck, what if I wrote this? Well, it's not really spelled that way, but I guess I'd live with it. Power's measured in watt? Watts. And then you can turn the page. Number 6. This was your stairway lab that you guys all did. How much power does someone climbing stairs? Now, how many stairs did they climb, Michael?
82 stairs.
How many seconds?
82.
They're basically going 1 step per second. Is that terribly fast? Would you find this terribly tiring? I don't think we're going to get much power. In other words, most of you found you generated around 750 watts, around 1 horsepower. I think this is going to be smaller. I got already kind of a built-in gut instinct here. Power is going to be work over time. The work is going to be mgh over time. 64 G 9.8. It looks like the height is 82 stairs. 0.2 what? Not 21. We don't do physics with centimeters. Meters. 83 seconds. 64 times 9.8 times 82 times 0.21 divided by 83. Yeah, I figured it'd be small. 130 watts. You know what? Probably you could walk this flight of stairs at this pace for like 20 minutes without really, like, you'd be tired a little bit by the end because you'd be sick of stairs, but it wouldn't be like you'd be sweating or huffing and puffing. One step a second. Step, step, step. Well, okay, maybe after a few minutes you'd be tired-ish. 130 watts. Number 7, lifts tells me I am doing work. In fact, power is going to be work over time. It's going to be mgh over time. It's going to be 25 times 9.8 times 24 divided by 32, which also is not terribly fast. I'll go 184 watts. I'd even take 180 watts. I would take 183.75 watts. B says, what's the efficiency? Well, efficiency was that symbol. Except it should really connect right there. Or you could write the word efficiency or EFF, but if you want to be a nerd, you can use that. And it's going to be power out divided by power in. You know what? It's going to be a smaller number divided by bigger number. Smaller number divided by bigger number. Priya, it's going to be 184. Actually, I'm going to use 183.75 divided by, and they are both watts. I made sure the units matched because that's really the only mistake you can make here. Oh, how do I change 0.75 to a percentage? If you can do it in your head and you can just say 75%, I'm fine with that. Otherwise, times it by 100. How efficient is this? That there, by the way, Matteo tells me if these numbers are from real life, that's not a gasoline engine, that's an electric motor, because gasoline engines are way less efficient than that. Most of the energy goes to heat and sound. So why do we use gasoline engines? The fuel itself, gasoline itself, is a very efficient energy storer. The amount of energy stored in a liter or a gallon of fuel is an awful lot, and the fact that it's liquid means it's fairly easy to transport and store, and so that's part of our infrastructure. But probably in your lifetime, you'll be the generation that sees us move away from internal combustion to, electric vehicles are the dominant vehicle. I hope. Oh yeah, I took one for a test drive this summer. They are, unicorn tears and rainbow dust. It's amazing. Ready? How much work? Well, the work done by the applied force is probably going to be the applied force times distance. We're pushing something horizontally. The distance is horizontal. So I double-checked, Tori. The force and the distance are in the same direction. So it's going to be 65 times 14. Can I do that in my head? It's going to be 650 plus 130 plus 130. 650 plus 130 is going to be 780, 880, 910? No.
Yeah.
Yeah? 910 joules of work. Except not all of that. Now we can start to talk about work in terms of energy. Not all of that energy, Julie, went into making this mass speed up. Not all of it went into kinetic. Some of it went into heating up the floor. It would be the work done by friction. That's going to be the force of friction times distance. Quick free body diagram. Gravity down, normal force. There's the applied. Friction. Friction is what times what? Well, that's going to be mu times the normal force times distance. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Mu mg times d. How much energy did I lose to friction? 0.25. Mass 12. 9.8 times 14. Do that one in your head. A little yucky. I think I probably could if I really had to, because multiplying by 0.25 is the same as dividing by 4, so that's 3 times 9.8 times 14. 411.6? I'm going to write 412 joules. I take 411.6. That's lost energy. You can sort of think of that as negative in that you've lost energy. Not negative in terms of north, south, east, or west, but in terms of, hey, I started out with 910. I gave 412 joules into heating up the floor. What's my net work? It's going to be 910 minus 411.6. That's how much energy was left over for what you're pushing. Where did that energy go? Kinetic. That's the energy that's causing this object to speed up. 498.4 joules. I would take 498 joules. 1 mark. Can you give yourself a lovely score, please, out of 13, apparently, and then pass them inwards? So what have we been saying? The law of conservation of energy says that the amount of energy you start with is equal to the amount of energy you end with. You can do it mathematically, algebraically. You can plug in all the numbers and just like, how much kinetic do I have? 5,000 joules. How much potential do I have? 4,000 joules. Where'd that extra 1,000 joules go? You can do it that way. I do it algebraically unless they get really, really yucky. So we looked at slingshots. We looked at rope swings. Slap shots were a great example. Roller coasters. Oh yeah. Gilon, I'm coming at you. Here's our roller coaster. Says this, the roller coaster below has a mass of 255 kilograms. Check. If the roller coaster just barely makes it over the first hill, in other words, let's assume that right now VI is 0, which is not a real roller coaster. In real life, on that top hill, you do have some speed, but we're going to start off easy. How fast will it be going at B? I think Gilon will call this initial, we'll call that final. Yes? Is there a change in height in this question? Yeah, is there a change in speed in this question? Is there a yucky, curvy path? This is a job for conservation of energy. As soon as you give me something like that, I want a scalar approach, not a vector approach that has to change direction all the time. Am I hearing someone's phone?
No, it's my alarm for 6:30 in the morning. I don't know why it's going on. Oh.
We'll just pause the video for a second. Let's continue. Suddenly I lost everything. Where'd everything go? I don't know. Let's find out. Come back. There we go. So I'm going to start out, Gilon, with conservation of energy. Kinetic, initial, potential, initial equals kinetic, final, and potential, final, plus... Oh, wait a minute. Am I going to write plus heat? Gilon, what does it say in brackets? Oh, right, next to the bracket. Ignore. Oh, so no heat. Okay. Gilon, are any of these 0? Let's do kinetic first. Am I ever stopped? Am I ever at rest? When? Cool. What about potential? Am I ever on the ground? You know what? Since 2 things have canceled and I only have 2 things left, I'm going to do this algebraically. This is an easy one to get the whatever by itself. Potential energy, that's mgh, and this is going to be a half mv final squared. Gilon, have you gone on a roller coaster before? Yeah. When you went on the roller coaster, did they make you step on a scale before you got on the roller coaster? Did they weigh you? No. You know why? Right there. Mass cancels. And again, Karn, I'm fibbing a bit. In real life, there is a bit of friction. There is heat, and when there's heat, the mass doesn't cancel. But if we grease everything down and make the friction as little as possible, although the mass technically, Julie, doesn't cancel, it becomes negligible. An empty car and a full car will make it through the track. How many of you have been on California Screaming? The one at Disneyland, okay? You may notice one way you can tell the mass doesn't cancel. At the very end of the ride, they actually have to slow you down. That's because there is some variation in your final speed because there is some friction. Otherwise, it's still a pretty good roller coaster. I give it a thumbs up. What am I trying to find, Jilin? Oh, how would I get the v by itself? I've told you I think about that 1/2 in two ways. Sometimes I think about it as a 0.5, and you could divide by 0.5 because it's timesing. Or I think about it as a times by 1, divide by 2. Here, I'm going to think about it as a times by 1, divide by 2, because timesing by 1 would mean dividing by 1. Dividing by 2 means on this side, timesing by 2. I get 2 GHI equals VF squared. VF what? Squared. Jilin, how to get rid of a squared? Yes. Here we go. How fast am I going at the bottom if assuming I start from rest? Which in real life I don't. 2 times 9.8 times, is 18? Is the height 18?
Yes.
Yeah? Okay. I've scrolled down. Square root of that. 18 point, I'll call it 18.8 meters per second. Times by 3.6, about 70 kilometers per hour. That's pretty good. I've been faster. Well, first of all, this one is unrealistic because, Connor, I have you starting at rest. Part B, let's give it an initial speed of 22 meters per second. Let's say this is like the second hill that you're going over, not the first one. So you've got some speed. How fast will I be traveling at B? Connor, is there a change in height?
Yep.
Is there a change in speed?
Yep.
Is there a yucky curvy path? I'm going to use conservation of energy. Kinetic initial, potential initial, kinetic final, potential final, and it says ignore friction, so to heat. Connor, are any of these 0? This time the kinetics sadly are not.
But yeah.
What's 0?
Yeah.
Okay. How many terms do I have? 3. You know what? I think I'll do this one algebraically, but this is right around my tipping point threshold where sometimes, Kayla, you'll see I actually start plugging in numbers and then just get the final thing, like gather like terms, and I solve it like grade 8. And sometimes I do it algebraically. It's right around my limit. But here, this is going to be a half m v initial squared plus m g h initial equals a half m v final squared. By the way, if you had some speed at the top of the hill, at the bottom, do you think you're going to be going faster than 18.8 or slower than 18.8? Yeah, I'm hopefully way faster. Let's find out. Connor, have you been on a roller coaster?
I have.
Did you have to step on a scale before you got on the roller coaster?
Did not know.
Cool. Connor, what am I trying to get by itself?
The V F.
This is where instead of a 1/2, I might actually treat that as a 0.5. And I might say, hey, divide by 0.5, because it's timesing by 0.5. That gives me VF squared.
Square root.
In other words, I think I end up with this. The final speed at the bottom is going to be 0.5 times my initial speed. What was my initial speed? This was it 22?
Yeah.
Squared plus 9.8 times 18, all divided by 0.5, and then I'm going to take the square root of that answer. Is that okay, Cassidy? You get your name right? It's those little things. Connor, is this a fraction?
Yes.
So top brackets, yeah? Bottom, 0.5, don't need brackets. This is one, again, folks, these are worth trying to type in, practicing to type in on your calculator. Probably want your calculator out rather than your phone out, not mentioning any names. Nice stretch. 0.5 times 22, because it does me no good if you can write everything, but you can't get the right answer. Ooh, I like that. 28.9? Or if I want to go kilometers per hour, just over 100. Now that's a good coaster. Now we're doing freeway speed. Still not, I mean, there are faster, right? Last I checked, it was the top flight dragster at Cedar Point, which did crack to 100 miles an hour. But they may have beaten that, because there are these coaster wars literally going on, where as soon as an amusement park opens a bigger and better, the next group opens a bigger and better. So what were you going to say?
I think maybe Formula Rocks and Abu Dhabi.
I haven't done a Google search in about a year or two. I need to go look.
Yeah. I don't know, later on.
Anyways, 28.9 meters per second. Is that okay, Nick? Now, in real life, you're not going to be doing 28.9. This is in our magic physics world with no friction. So let's suppose that, you got to turn the page. Suppose the roller coaster in part B is only traveling 25 meters per second. Mr. Dewick, how would you figure that out? Oh, pretty easy. You'd stand at the bottom of the roller coaster with your radar gun, and you'd clock it as it came by. Yeah, we bring one of these with us to Playland Physics. Of course we do. Why would you not? By the way, if you think going to an amusement park is fun, wait till you have data. When you have data and an amusement park, it's just, anyways. While you're standing in line, you can calculate how fast you're going to be going when you get to ground level. Oh, it's good stuff. Just adds to it. Okay. How much energy was lost to heat? Well, still a change in height, change in speed, curvy path. Adrian, this is a job for conservation of energy. Except now I'm going to have KE initial, PE initial equals KE final, PE final, but this time Adrian plus heat. Is that okay? Adrian, you good? Okay. I still think that's going to be 0. Adrian, what am I trying to find here? Heat. That thing? How would I get the heat by itself? How will I move this KE final over? Yeah. For some reason, the most common mistake kids on this particular question, I like this question, for some reason, they divide by KE final. Even my physics 12s, I see it. And I'm not sure why. So Adrian, I think it's going to be this. KE initial, PE initial, minus KE final. That's going to be, I'm going to put the heat on this side by itself, if that's okay. So it's going to be a half m v initial squared plus m g h initial minus a half m v final squared. Adrian, is there an m in this last term?
Yeah.
Is there an m in this middle term?
Yeah.
Is there an m in this first term? Is there an m in heat, though? This is why in real life, mass doesn't quite cancel. But again, if I can get that heat near to 0 stage, then the mass really becomes negligible. I'm going to do heat in red. Heat. 0.5. Now I do need the mass. What was it? Can someone turn back? 255? Thank you. And I think our initial we said was 22? Yeah? Squared. Plus 255 times 9.8 times 18 minus 0.5, 255, 25 squared. You can probably type that in one big line on your calculator if you got a good calculator. Hopefully I've gone on the occasional rant about good calculators. It's going to be 0.5 times 255 times 22 squared plus 255 times 9.8 times 18 minus 0.5 times 255 times 25 squared. Last class I totally botched typing this and made 3 mistakes. Let's see. Is that right? 27,000? You know what? I'll call it 27,000 even. Yes? No?
Yeah.
Units. Heat. Joules. Energy. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. By the way, these were the ancestors to roller coasters. The first roller coasters were just a straight ramp. It was often called a chute or something like that. They were often old mining trains. And so similar to the way you guys do water slides now, you would physically climb up a ladder or climb up some stairs. You would sit in a little cart and then whee, you would go down the railing. Those were around 1890, 1900, 1910. Then they started building amusement parks. The first amusement parks were all built at the end of subway lines. Why were they built at the end of subway lines? Because subways were owned by electric companies because they were the first big electric apparatus in society, but nobody rode subways on weekends, and the subway companies needed to give people a reason to ride subways on weekends because they wanted to make their money because they had to run the subways anyways, so why not get them as full as possible? Let's put an amusement park line at the end. That's why Coney Island and all those classic amusement parks, if you look at where they are, why they are, they're at the end of a major subway line. We'll do amusement park history in Physics 12 because we'll be going to one. Anyways. Julie, what's A want me to find?
Energy loss.
Okay. Is there a change in height in this question? Is there a change in speed in this question? Yeah. Is there a yucky, curvy path? No. Wait a minute. Are they asking me to find energy and heat? Hey, that's also a job for conservation of energy. So my little checklist doesn't always work, Kayla. We're broadening it now, but okay. In other words, I think I'm going to write the same thing as I did before. KE initial plus PE initial equals KE final plus PE final plus E. Julie, are any of these 0? Yep, because it does say from rest. Because we're ending up on the ground. Oh, this is actually not too bad. How would I get the heat by itself? So if I hear you, you're telling me the PEI, Prince Edward Island, would stay where it is, minus KEF? Yeah. So it's going to be mgh initial minus a half mv final squared. Do the masses cancel here? There's no mass in heat, so no. We are now at the plug and chug stage. I hope. It's going to be 0.5, not 0.5, m. What was the mass? Oh, 75, there it is. 75, 9.8, 20, minus 0.5, 75, 15 squared. 75 times 9.8 times 20 minus 0.5 times 75 times 15 squared. Do you get 62, 62.5? No? You got, yeah? Anybody else? Yeah? Okay. I'll write down 6260, but I'll keep this on my calculator. Julie, here is the curveball, part B. What does part B want me to find? Average force of friction. Now, normally I would say friction is what times what, and you would say mu times the normal force. But wait a minute. Did this question give me a mu? No. Any ideas? What? Hey, Connor is clued in that often the curveball question requires you to use something you just figured out. We did just figure out heat. And you know what? Another way to think about heat is this is the work done by friction. So you said work is force times distance, I'm telling you, Julie, the work done by friction is going to be the force of friction times distance. And this is kind of cool because this is the first time we're calculating friction. We're calculating it on a slant and without a mu. Okay. Julie, how would I get the force by itself?
Divide by three.
Yeah. Friction, by the way, the reason I said average force of friction, I'm not sure it's constant. It may depend on how fast the car is going. I don't know. I'd have to run some numbers. It's going to be work done by friction over d. What's the work done by friction? Another word for that, Karn, is heat. 62, 62.5. And now, Julie, here's the next question. Which distance do you think I want to use? Because the 60 is in the same direction as the friction force. That's why they gave me that 60. $104.3. 104. 104 what, Julie? It's a force. Yep. Yep. In Physics 12, we will actually give you a method to deal with slantiness, with inclines. We'll do like 3 or 4 days on it. That's the big difference between Physics 11 and Physics 12. You'll find in this case, the normal force is not mg, and we have to do some modifications to our equation. But using a scalar approach, we did okay. Yeah? Okay, you can relax now. But you can turn the page too. Who knows what a Rube Goldberg machine is? You do? They're also called chain reaction machines. Rube Goldberg was a cartoonist in the 1940s and 1950s. He was an illustrator. And he was famous for doing the back of magazine covers or newspapers, or quite often the Saturday Evening Post or the New Yorker, where he would draw an elaborate machine that was designed to do a simple task. The task might be make toast. But you would pull a lever, which would knock something over, which would roll a ball, which would light a match, which would burn a candle, which would scare a mouse, which would make a bird fly. Just these elaborate chain reaction machines. And although he only drew them, he never built them, people have been inspired to try and build their own. And we name them in his honor. We call them Rube Goldberg machines because he was the illustrator who popularized the concepts. They are great examples of conservation of energy transformations. That Honda commercial that I showed you a few days ago was that you saw in the video when I was at Playland. That was a good example of a Rube Goldberg chain reaction machine. Oh, here's another pretty good one. Put your pencils down, look up. Ty, sit up. Pick your pencils up. Last class, we did the bouncy ball shtick, but I didn't talk about the very, very bottom here. A golfer wishes to hit his drives further, and the way to do that is to increase the kinetic energy that the golf club has when it strikes the ball. Which would be a better effect, have a greater effect on the energy transferred to the ball by the driver? Doubling the mass of the club head or doubling the speed of the club head? Why would doubling the speed have a way bigger effect?
It's square.
If you can get the club head to go twice as fast, the golf ball will go 4 times further. If you made the club head twice as heavy, the golf ball will go twice as far. And this is why, even though heavier does also make it go further, we've made the clubs, we've made the hockey sticks, we've made our equipment, tennis rackets, lighter. We'll sacrifice a little bit of the mass aspect because, boy, anything we get out of club head speed, out of racket speed, out of stick speed, way faster. That's squared. That's squared. What's your homework? But I have a present for Rio and all of you.